Hello and welcome to another LeetCode problem. So we're going to be doing problem number 1214, two-sum BSTs, which is the premium problem of the week. And so in this problem, you're given two roots of two BSTs, and you want to return true if there's a node in the first tree and a node in the second tree whose values sum up to a given integer target. And so for this example one, we'd have these two trees, we'd have a target 5, and we do definitely have values for that. So we have a 3 and a 2 that sum up to a 5. Then in the second one, we want target 18, and we obviously don't have that because the biggest value we have is 7 and a 10, so it's only 17. So how would we do this problem? And there's actually a couple ways, so let me show you. I'm going to describe one way, and then we are going to do the other way, which doesn't take advantage of the fact that we have BSTs. However, I think it's faster overall. So one way is pretty straightforward. What we can do is we can actually iterate through every single node in the left tree. So like, let's say we're at this node, and we could figure out, okay, like let's say target is 5. What value do we need to find in this tree? Well, it's pretty straightforward. We would need, so what would we need? We actually would need a value 3, right? So 5 minus 2. So we need 3. Then we can just search through this second tree, and it's going to be a logarithmic search because it's going to be like a binary search. So we can just search through the second tree and see, do we have a 3? So we'd start at the node, we'd start at the root, and then we can go to all the other nodes. So that'd be one way of doing it, whereas like, and then for every, we have to do that for every single node in the left tree, right? So like if there was no combination here, we'd have to try something here. We'd have to try like, is there a 3 here? And we'd have to, go search down the tree. So what would be the time complexity for that? Well, let's say this is n and this is m. For the tree on the left, worst case scenario, we have to search through every node. And then the tree on the right is actually going to be log m. However, what we're actually going to do instead is we're going to do something like our two-sum problem to make it even simpler. So the original two-sum, how does it work, right? You have an array and you try to look for two numbers and you ask if they add up to target. So we have these numbers, right? Like 1, 2, 3, 4, whatever. And we try to add them up to target 5. And the way it works is we search through the array and we keep adding the numbers into some hash map, right? That's how it works. So you have some hash map, and then you add the numbers into it. And then at every index, you just say like, hey, is target minus index in there? So we can actually do the same thing for these two trees. So for these two trees, we can actually traverse both trees, and we can get the sets, or sorry, we can get the numbers that are in both trees in two different sets. So let's just say we have like L, which is a set, and then it's going to have the numbers that are in the left set. So let's just say that's 1, 2, 4. Then we have the right set, and that's going to be 0, 1, 3. The word doesn't matter. So once we actually have that, it's pretty straightforward, right? We have two sets and we have a target. Then all we have to do is loop through this left set, and then for every single one of these numbers, we can just ask, is the target minus the left in this, right? So what we do is we try the 1, and we'd say, okay, let's say target is 5. We'd say, is 5 minus 1 in this right set? Well, 5 minus 1 is 4. 4 is not in the right set. Okay, let's try 2. So for 2, 5 minus 2 is 3. Is 3 in the right set? Yeah, it is. Okay, perfect. And if we loop through the left set and the target minus the number is never in the right set, then we have no solution. And so the time complexity of that is we have to iterate through this whole tree, we have to iterate through this whole tree, and we have to save all the numbers in both trees. So worst case, that's going to be m plus n time, and m plus n space, assuming every single number is unique. But that's going to be better than the binary search way, where that's going to be m log n, right? Like this is smaller on average. Obviously, there are like worst case scenarios where this one is actually smaller for sure, right? But, on average, this one's going to be better. And so we're pretty much doing the same thing that we're doing in a normal two-sum, except now we just have two sets instead of yeah. We actually don't even need two sets. Yeah, we can actually do it a different way. So instead of actually having two sets, we can just traverse one tree, save it in a set, and then we can just traverse the other tree. And while we're traversing the other tree, then we can just check for all those values. So yeah, let's just do that. Then actually the time complexity there, so if this is m and this is n, then the time complexity will still be n plus m, but the space complexity would only be m, right? So we just pick one, save it, and then traverse the other, and we can do it in the traversal. So let's do that. It's a little bit more code to do that way because I was going to use a helper function to traverse both, but let's do it where we just traverse this one on the right, store in a set, then we can traverse the one on the left, and yeah, and then we can just look for the result. Okay. So let's see how we would do that. So first we need a helper function, right? Some kind of recursive traversal. So def traverse node. And then we need a set. So we're going to read like right nodes or something equals set. So def traverse node, pretty straightforward algorithm here. So if not node, we just return. Then we just write nodes dot append. It's not going to be append, it's going to be add. Node dot val. Then we just check the left and the right. So traverse node dot left, traverse node dot right. So now that we have this right filled out, now we need another function that's going to traverse the left. And then what we need to actually do, we can do it recursively as well. What we can do is we can just, so we can traverse the left, and then as soon as we find a matching value, we can just exit immediately. So that would be fine too, right? So we can have some check or something, right, to see if there was a target. So check, or we can just return true straight away. So we could return true and false. We can just return true straight away. That would work too, right? So let's do that. So we need another function. It's not like traverse, it's going to be something else. So let's just call it def numcheck maybe. And it's going to take a node as well. So if not node, we're going to return false here. Okay, if target minus node.val. If target minus node.val is in right nodes, we can return true. Yeah. And then we can also return either the left or the right. So we can just return, numcheck. And then this is going to be node.left. Or if it's in one of those, just return check node.right. And so there you go. So we could just do it this way, and now we don't need another set. I think actually the space complexity is going to end up being, now that I think about it, it's going to end up being the same worst case, but whatever, this is fine. Okay, so now we just do that, and I think we're done. So now we simply call traverse on the right root, and now we just return numcheck on the left root, and I think that should do it. If I could write things correctly. Let's see here. So right root is actually root 2, and this is root 1. Okay. So that actually worked, and it was pretty efficient. And so let's think of the time and space complexity here. So the time, actually, worst case scenario, we would have to check the nodes of both, right? Like we always have to check all the nodes of the right tree no matter what, because this traverse is going to traverse the right tree. But for the left tree, worst case scenario, let's say the number is like the last node we visit that we were trying to find. So that would be m plus n, where m is the, let's say, length of the left tree and n is the length of the right tree. And for space, we have to store m because that's, or we have to store n because that's going to be all the right nodes. And then I think m can actually be worst case. We do have to store the entire tree. And that would be in a case where, let's say, our tree looks like this. But I think on average, we're going to do better than 2 sets. But let's say we have a tree like this. So this is our tree, and then the target node is here. Our recursion stack would actually be, the length of this whole thing. And so that if that's m, then that's going to be m. But on average, it's going to be significantly better than that. It's going to be like logarithmic or we find something right away, we're saving a ton. So on average, it's much better, but worst case scenario, it's the same. Okay, so hopefully you like this problem. It was definitely a nice variation of twosome. Not super tricky for sure. Like, I'd say it's more of an easier medium problem, but yeah, if you like this problem, please like the video and subscribe to the channel, and I will see you in the next one. Thanks for watching.